Now this example is pretty cool. It is the indefinite integral of the product of x and e to the power of the square root of 1 plus x squared dx. Now here, because of this form here, 1 plus x squared, well, the square root of 1 plus x squared, immediately my mind goes to a trig substitution. And that trig substitution is let x equal a times tangent of theta. Now, a is the number whose square gives me 1, so a then is 1. So I'm going to go ahead and just erase a, because a in this case is just 1. Okay, so if this is my trig substitution, then, well, there's a lot to be said here. First of all, let's see if I can get this. All right, dx, the derivative of x with respect to theta will be secant squared of theta d theta. Okay, so then what we have then is this integral that is tan theta, because that's what x is, times e to the power of the square root of 1 plus x squared. But if x is tan theta, then that's 1 plus tan squared of theta. And then this is secant squared of theta d theta. Okay, remember that by the Pythagorean identity, 1 plus tangent squared of theta is equivalent to secant squared of theta. So then this is tan theta e to the power of the square root of secant squared theta. And then we have down here secant squared theta d theta. Simplifying more, this gives us the indefinite integral of tan theta e to the power of just secant theta, and then we have secant squared theta d theta. Now, what I'm going to do here is I am going to, yes, we are going to integrate by parts. Okay, so with parts, I want to choose something for u and then something for dv. I think what I want to choose for u is secant theta. So if u is equal to secant theta, keep in mind that you have a secant theta up here, so that'll be u. And one of these will be u, leaving me with another factor of secant theta, okay? So du would be equal to secant theta, tan theta, d theta, that's the derivative of secant theta. That would mean that dv is equal to, so I already have e to the power of u here. I have one of these secant thetas called u, so that leaves me with tan theta, the other secant theta, and then d theta. All right, which means that v is secant theta, because this here is the derivative of secant of theta. All right, so let's now rewrite our integral, okay, with this in mind. Now you have the integral of, now u is secant theta, okay, so one of these secant thetas is called u, okay, and then you have e to the u, and then the other secant theta, tan theta, d theta, is actually, oh, it's right here, is du. Now, I'm hoping that this looks really familiar to you. In class, we saw something like this: the indefinite integral of x e to the x dx. Check your notes, please. But when we did this integral in class, we found that this is actually equal to x e to the x minus e to the x plus c. This is exactly the, sorry, that's really sloppy. It's supposed to be a plus sign right there. This is exactly the form that we have this in. So that's what I'll use. So then this here is equal to u e to the u minus e to the u, and then of course plus c. I'll put the plus c on the end. Okay, so please check your notes. We're taking advantage of us already doing this, okay? Now, let's remember what u is. It's still on the screen. I almost scrolled too fast here, but u is secant theta. So let me rewrite this. So then this is secant theta e to the power of secant theta minus e to the secant theta. However, this problem came to us in terms of x. So we need to put this in terms of x. But remember, I can scroll up, but I'll just remind us that we chose x to be tan theta. So if I draw a reference triangle and call this theta, then tangent of theta, which is opposite over adjacent, must be equal to x. So that means the opposite side is x and the adjacent side has to be 1. That way, tangent of this angle theta is x over 1, which is just x. But by the Pythagorean theorem, that makes this hypotenuse side the square root of 1 squared plus x squared. Therefore, our final answer is secant theta, and if you look at your triangle, secant theta is the hypotenuse over the adjacent side, which is just 1, times e to the power of secant theta minus e to the power of secant theta. And then, of course, plus c. And if I can just kind of move this out of the way here, because this is my final answer. I like this problem because it used what we've seen before, used kind of what we've proven already. All right, cool. That was fun. Let's look at the next example. Okay, check out this one. The indefinite integral of the natural log of 1 plus x squared dx. Now, I want to do this by parts, but remember by parts is only for integrals that involve a product. But this is really the product of the natural log of 1 plus x squared times 1 and then dx. So then I'm going to choose this. I'm going to choose u to be the natural log of 1 plus x squared. Okay, that would mean, and then I'm going to choose dv to be 1 times dx, which is just dx, meaning that v is equal to just x. Okay, over here, du would be equal to, the derivative of the natural log is 1 over the argument, so 1 over 1 plus x squared, times the derivative of the inner function, which is going to be the derivative of 1 plus x squared, which is just 2x. Let's not forget dx. So let me clean that up a little bit. Du is equal to 2x over 1 plus x squared, and then dx. Okay. All right. So then that means this right here implies that dx is equal to 1 plus x squared over 2x du. Actually, I think I did too much. I don't think I needed to isolate dx here. That was a mistake. Let me erase that. Okay, cool. So I have it. So let's now rewrite our integral by parts. Remember that, let's see if I can, well, I'll squeeze it in right here. Remember that it is uv minus the integral of v du. So I'm going to use that pattern here to write down my new integral. Okay, so u times v in this case would be x times the natural log of 1 plus x squared, okay, minus the integral of v du would be x times du, there it is, 2x over 1 plus x squared, and then dx. All right, if I can move this screen up, sorry. All right, I just minimized that or made it a little smaller. So then this is x times the natural log of 1 plus x squared minus the indefinite integral of 2x squared over 1 plus x squared dx. Excellent. Now for this integral here, we can use a trig substitution. Let me get that up on the board. First, x times the natural log of 1 plus x squared, copy that down, minus. Now here, what I can say is, and I'm thinking a trig substitution because of the form of this 1 plus x squared. So I'm thinking of x is equal to tan theta. That would mean x squared is equal to tangent squared of theta. Furthermore, dx is equal to secant squared of theta d theta. So with this substitution, I would have, I'm going to actually pull out the 2, okay, folks? The 2 that's in the numerator. And that way in the numerator, you just have x squared, which is tangent squared of theta, over 1 plus x squared, which is 1 plus tangent squared of theta, and then dx is secant squared of theta, d theta. So what that'll do for us then is I'll have x times the natural log of 1 plus x squared minus 2 times. Now, let's not forget the Pythagorean identity that says 1 plus tangent squared of theta is equal to secant squared of theta. And then times this secant squared of theta d theta that we have here. So that this secant squared of theta and this secant squared of theta actually cancel. And then I'm going to rewrite tangent squared, and I'm going to use a Pythagorean identity that says that tangent squared is equal to secant squared of theta minus 1. I'm talking about this Pythagorean identity. So that must mean that tangent squared of theta is equal to secant squared of theta minus 1. So that's what I'm going to use here. So therefore, I'm going to have x times the natural log of 1 plus x squared minus 2 times the indefinite integral of secant squared of theta minus 1 d theta. Okay, and we can integrate term by term. So then this is minus 2 times the function whose derivative is secant squared of theta is tangent of theta. And then this is going to be plus 2 theta. Okay, this 2 is being distributed, and this negative and that negative make a positive. Now, excuse me, what we want to do here is make sure everything is in terms of x. Now, the first 2 terms are, but the second 2 terms are not. So let's remember what we said earlier. We said x is equal to tan of theta. So again, we have this reference triangle. We made it earlier. So if this is theta, then this is x and this is 1. This is the square root of 1 plus x squared. Furthermore, this statement right here implies that theta is equal to inverse tangent of x. Okay, so let's fill this in. So the final answer then is, let's see if I can fit it in right here, x times the natural log of 1 plus x squared minus 2 times tan theta, which is just x, plus 2 times theta would be 2 times inverse tangent of x. And then I'll finally put my plus c on the back end. All right, there we have it, folks. All right, this one actually looks a little familiar, but we haven't done it before, but it just looks familiar. So we have the indefinite integral of x times e to the power of the square root of x dx. So the first thing that comes to mind is probably making a u substitution. And I'm also thinking about parts because this, after all, is a product. It's x times e to the power of the square root of x. So we definitely have a product, which is leading me to the integration by parts. But first, how about a u sub? So a u sub, if I say let u equal the square root of x, that would imply that u squared is equal to x. That's helpful. Also, what that would imply is, let's see, du is equal to, remember that this is x to the power of 1/2. And so, therefore, it would be 1 over 2 root x, like that, dx. Matter of fact, you know what? I think it would probably be better. Let me erase what I just wrote. And I think it might be better if, well, first of all, I can get this eraser to work. Oh, okay, there we go. I think it would be better, look at the second statement. And if we integrate both sides here, so this would be 2, so let me say this implies that 2u du, I guess I can write that nicer. 2u du is equal to 1 dx. What I did right there is differentiated both sides. Okay, that is going to be helpful. So let me rewrite my integral now with this u substitution. I have the indefinite integral of u squared, and I have e to the u, and then dx is 2u du. So that can be rewritten with the 2 on the outside, of course, and u squared times u is u cubed, and then I have e to the u du. That's nicer. Now, let's integrate by parts. Now, let's choose, I'm going to choose, let's see, remember I need something for u, I need something for dv. So I'm going to choose u to be u cubed. That means du would be 3u squared du. And then I'll choose for dv e to the u du, which would mean that v is equal to e to the u. Okay, so with this in mind, I guess I can keep scrolling there. With this in mind, I can rewrite this as, let's not forget that there's a 2 on the outside of everything, okay? U times v would be u cubed times e to the u minus the indefinite integral of v du. In this case, it would be 3u squared e to the u du, like that. Okay, this is integration by parts. Okay, all right, I'm just going to rewrite this just a little bit here. So then I have 2 times u cubed e to the u minus 3 times, and then the indefinite integral of u squared e to the u du. Okay, so I believe we're going to need integration by parts again. So let's try it again. So this time, I have u is equal to u squared. That would mean that du is equal to 2u du. Okay, And then what I'll choose for dv is e to the u du, like I chose earlier, which means v is just e to the u. Okay. What that will do then is I'm going to use integration by parts again. So it's 2 times u cubed e to the u minus 3 times, I'm going to open up a set of parentheses. So it's uv, which would be u squared e to the u minus the indefinite integral of v du, which would be 2u e to the u du. All right, excellent. So let's see what we should do next. I think we should expand. What I'm going to do is I'm going to factor out this 2 right here. Let me do that really quickly. U cubed e to the u minus 3. I'm going to go ahead and distribute this negative 3. And at the same time, I'm bringing out this 2. Okay. So minus 3 u squared e to the u. It'll be plus 6 times the indefinite integral of u e to the u du. Now, let's remember that we know what this is, right? We've done it in class, and it even came up in this lesson here as a recall. So let me copy this down first. E to the u, and then plus 6 times. All right, here we go. Now, this here is integration by parts, but we did it in class. It is u e to the u minus e to the u. Like that. All right, let me close all of that. Okay, make sure I have everything. Okay, what I'm going to do now is I am going to distribute this 6, and I'm going to distribute that 2. So I have 2u cubed e to the u minus 6u squared e to the u plus 12u e to the u minus 12 e to the u. Excellent. Now, I'll put the plus c on the back end. Let's not forget what we chose for u in the beginning. We said in the very beginning, we said let u equal, we said the square root of x, which let's not forget that x is the same thing as x to the 1/2. So if I put everything back in terms of x, this would be 2 times x to the 1/2 cubed e to the power of the square root of x minus 6 times u squared would be the square of the square root of x, which would just be x, e to the square root of x plus 12 times the square root of x, e to the square root of x, minus 12 times e to the square root of x. Sorry for that kind of slide. Let me get rid of this yellow, because that was just us remembering what we had already said. Let me get rid of that. All right. Let me clean this up a little bit. So then this is 2x to the 3/2 e to the square root of x minus 6x e to the square root of x plus 12 times the square root of x e to the square root of x minus 12 e to the square root of x, and then of course plus c. So this was an example of integration by parts multiple times over. It was fun. I really like the answer. It's like, I know it seems long and complicated, but it's kind of cool that we got such a long answer. All right, cool. I hope you took really good notes, and that you, at the end of the day, I hope you see the different integration techniques or strategies that we used. Integration by parts, of course, partial fractions, trig substitutions, and even rewriting the integrand using our fundamental trig identities.